Hello, Mr. Sanderson here. In this video, I want to take a look at some key concepts that help us understand circular motion and when the motion is vertical. So we were talking about horizontal circular motion where the car might be traveling on a level surface, going around in a circle, and we know that the force had to be directed inwards to keep that car moving around in the circle. But that was the center directed force, that net force to the middle. But when we are looking at a circle that is now vertical, like in this roller coaster, where once they go down the dip and come back over the hill, those can be also modeled as circular motion, but we also have to look at the force of gravity because we know gravity is a vertical force. So that's going to come into play. All right, so let's take a look at that in this video. I'm going to run through a couple examples. I'm going to have you fill out this conceptual chart with me. So have your notes ready, and we're going to take a look at how we can analyze this motion with vertical circles, knowing our acceleration and net force ideas. All right, so the first thing to take a look at is how can we analyze the forces that are acting on a roller coaster? Well, I know for sure that the force of gravity is going to be present. So the weight, which is equal to mass times gravity of that roller coaster, will be something that is present at any part along the track. So I know that that force, that downward weight force, would be at point A, and it's also going to be at point B, and it's also going to be at point C, and it's going to be the same amount of downward force because we're not changing the mass of the object and we're not changing the amount of gravity. We're still on Earth. Therefore, I know that force is going to stay the same at any point along the path. And if the cart is at the beginning where it's not on a curve yet, it's not going up or down in a circle, it's going to be resting against the surface of the track. And because it's not accelerating upwards or downwards, that normal force is going to exactly balance the weight force, just as if it was on a level surface. All right, well, things get a little interesting though when that car starts to move through the circle. We know from the horizontal circular motion that in order to maintain a circular path so that the car doesn't just continue in a straight line path, there needs to be a force that's accelerating it inwards. Well, that's going to be tricky because I already have a force that's accelerating it down. So I need to have a larger force that's directing towards the center in order to have a net combination of those forces that is an inward force. So where does that come from? Well, it turns out that the normal force changes. And when you're in the bottom of a circle like this and in this dip area, that normal force is actually increasing, and you will feel that by more pressure pushing against you, you're going to feel heavier in that part of the curve. Think about it. You might have been in a roller coaster where you get to the bottom of the dip and you start to feel that push against you. You feel heavier. It's because the normal force from the surface is now pushing more against you, so that the combination of that and the weight produces a net force to the middle. All right, so what's going to happen then as the cart rolls along to section B? Well, again, we need a net force to the middle. So right now I already have a net force to the middle, the FG. However, the cart is still on the surface. So the surface is still pushing against it. So there will still be some normal force, but it must be a smaller amount of normal force because I need the force net. When I combine normal and gravity force, I need the net force to be directed to the center. And the only way to do that is to have less normal force so that my overall net force is directed to the center, making it turn and accelerate around that corner. All right. Similarly, when I get to the loop-to-loop, I'm having net, having the force of gravity is already downwards, and if that was the only force acting on it, I would have a net force that is pointed to the center, so it would maintain that circular motion. However, there's also a surface force from the roller coaster tracks pushing into the cart, but since it's upside down, it's going to push downwards. So the normal force from the track will combine with the gravitational force to produce the overall net force around that loop-to-loop. All right, so let's take a look at this in a little bit more and fill in our charts. All right, so I know that I have different forces present, normal force and gravity, in each of the cases. I know that in order to maintain circular motion in this dip area, I need to have a bigger normal force because when I combine that with the weight force, I need a net force directed towards the center. So my normal force must win in this case. If I'm going over the curve, I need my net force to the middle to be larger to the middle, so therefore I need a smaller normal, and the weight's going to win. All right, and this actually does depend a lot on the location when we do the loop-to-loop. It depends on the speed. So if I'm going in really, really fast, that normal force is going to increase and increase and increase. If I'm going in not as fast, it's going to decrease. And in fact, there's a point where I wouldn't go fast enough to even make it around the corner. That normal force does change and changes a lot depending on the speed. All right, so when I draw the free body diagrams, I'm going to represent that as the normal force being larger when we're in the dip, and it's smaller when we're in the bump, and the weight force is always the same. I drew two instances here, one where it's not going as fast, and so it's a smaller normal force, and one where it's going a lot faster, where we have a bigger normal force. But notice they're both directed in the same way. So how do we analyze problems with this then? We need to find that force to the middle, that net force to the middle, by combining the normal force and the gravity. I think a good way to think about this is to take the big force minus the small force. So in this case, I'm going to have force normal minus my weight, and that will tell me the net force. If I'm going over the bump, like at point B, I have a smaller normal force, so I'm going to take the bigger weight minus the smaller normal force, and that's going to help me calculate the net force. And if I'm in the loop, I'm going to add these two together because they're pointed in the same direction all the time. So therefore, my net force to the middle is an addition of the normal plus the weight. And that's it. We can use that combination. Either we're taking the bigger normal force minus the weight, or the smaller normal force, and we take the weight force minus the smaller normal force, or we add them together in order to find out what our net middle force is that causes the acceleration. So what would it feel like? Well, if you have a bigger normal force, you're going to feel heavier, and because this force wins, it's going to accelerate upwards. If we have a smaller normal force, we're going to feel lighter, and since the weight force wins, we're going to accelerate downwards. And this last one, it really does depend on the speed. We may feel lighter when our normal force is smaller, or we may feel heavier if we're going really fast through that loop-to-loop, and the normal force increases to be bigger than the weight. All right, so that's how we're going to kind of analyze our situations. I want to show you one example using our force equations, right? Remember, weight is mass times gravity. It is a force measured in newtons. Friction is also a force that we can calculate, knowing the coefficient and the normal force. Normal force on a level surface, a horizontal surface, is mg, but it could be adjusted depending on where you're at and what the surface is, if it's horizontal or at an angle. And the net force, mass times acceleration, is our main force that we use, newtons, kilograms times meters per second. And if we have a net force to the middle, we're just going to tweak that slightly where the acceleration becomes v squared over r. So we still have a mass of the object moving in the circle in kilograms, the velocity of the object squared, divided by the radius, tells us the value of that net force to the middle. Now remember, that could be made up of these smaller individual forces, and that's what we're going to analyze in our problems. All right, so let's say, for example, we have a rider that is going through parts A and B, so a dip and a bump. Notice the free body diagram is different in each of those cases. At the dip, the normal force is bigger because we're heavier there. It's pushing back up. We have to direct our net force to the center by this force, the normal force winning. And at the top of the bump, the normal force is much smaller because the net center force must win, right? It has to be there, so gravity must be a bigger force. All right, so that's conceptually how we can do it. When we take a look at our problems, if I want to find the force of gravity, I'm going to multiply the mass times their acceleration of gravity, so I get 600 newtons. That's going to be the same in both cases. If we're going past point A and they tell us how fast we're going and the radius of that curve, we can figure out what the net force is to the middle. In this case is 2,500 newtons by taking 60 times 25 squared divided by 15. However, that is not the force the rider is experiencing. It's not their normal force, but it is the net force of directed to the middle. So how do I combine this in my net force equation? I'm going to take the larger normal force minus the weight force, and it will equal what we just calculated as the net middle force. So my 2,500 then is equal to the normal force minus 600. And if I do the math, I get a normal force of 3,100, which is a lot bigger than 600. So this person will feel really heavy at that point. All right, similarly, at point B, I can find out what the middle force is, the net middle force that's required to keep that moving in a circle. At that point is 432 newtons by taking 60 kilograms times 12 meters per second squared and dividing by the radius. That answer then is made up of the gravitational force, the weight, minus the normal force from the track. This one's bigger because it has to be directed downwards, and I can subtract then the normal force, and it should equal a normal force of 168. So I'm taking bigger minus smaller is equal to my net middle force. In this case, I will feel much lighter because my normal force is smaller than the 600, which is my weight. Please let me know if you have any questions on these. Give them a try, and I'll post the answer key in Schoology. Thanks, and have a great day.